Hello everybody. Today we are going to be going over electron configuration in an atom. So, first, what is electron configuration? We're essentially trying to give instructions on how to find an element on the periodic table. So, you have to know these couple concepts to be able to use the electron configuration. So, this here, this group 1 and 2, and helium. This is called the S group. They're the S block of the periodic table. Okay? This group, which is our transition metals, this is called the D block. These lanthanides and actinides are the F block. Here, I gotta use lowercase letters. F. And then the rest of these right here are the P block. So, that is fundamentally how this electron configuration is going to work. All we need to know this background information so that we can classify any element on the periodic table. So, let's say we want to find the electron configuration of hydrogen. So we're dealing with a neutral hydrogen, and so what the formula is going to be is we're going to have our n rows, and then our block, whatever block we're in, and then raised to the C columns. We'll just use F for families. So you'll see in a moment how this works. For hydrogen, we are in the first row. We are in the S block, and we are the first electron. This top number means how many electrons we have in that block. So in this case, 1s1. This would be the electron configuration of hydrogen. Now, what about helium? Try this one on your own. It's pretty similar. This would be 1s2 because there's 2 electrons in helium. Okay. Now, if you wanted to do lithium's electron configuration, what you need to do first is you need to do up to the noble gases electron configuration. So you have to start from the beginning. 1s2, that's helium, and then you're going to be in row 2, in row 2, and then you're going to be the first electron in that row. 1s2, 2s1. This is for lithium. Beryllium is just the same thing, 1s2 and then 2s2, because we're the second electron in the S block. Okay. So, let's move on to another couple examples in different blocks. So let's say we want to find the electron configuration for carbon, C. Okay. So first we have to put down the electron configuration from the start. So you're always going to start with 1s2, 2s2, and then when we go over here, this section right here, this is the P block on the periodic table, and that's where carbon is. So we're still in the second row. We're now in the P block, and we are electron 1, 2, so 2p2. So this would be the electron configuration for carbon. Okay. Now, what about neon? If we use neon, we have our electron configuration for 1s2, 2s2, and we're going to have 2, and we're going to be in the p block, and we're going to be the 1, 2, 3, 4, 5, 6th one in the p block. So 1s2, 2s2, 2p6. Okay. Now let's move on to some exceptions that come along with the transition metals. So for the transition metals, you can see that they start in row 4 of the periodic table. However, when we're classifying them, or when we're putting them in the electron configuration, the rows actually go like this. So it goes like 3 for these. It goes like 3, 4, 5. Okay, hold on. That's very messy. Well, I'll just write them here. 3, 4, 5, and 6. So those are the rows for the. You just got to remember, those are the rows only for the D block. So if you have potassium is still in n equals 4 row. So let's try. Let's actually show you something first, so that we can do this. We could do the more complicated examples. So first things first, we're going to, let's say we want to classify aluminum. This is going to take a while because we're going to have to do the electron configuration for many and many rows, and it'll take a while. However, we have a thing called a noble gas notation, where we put the electron configuration for the noble gas that was most recent, so i.e. neon. All this means is this is just a shorthand notation for the electron configuration of neon, and then you just fill out the rest of it. So we're going to be, the next thing is going to be sodium and magnesium, so that's going to be 3s2. And then we're going to have 3p, and since we're aluminum, we're the first electron. So this is a quicker way to actually describe the electron configuration. Let's try another example. Let's say we want to find Vidium's electron configuration. So it would just be the most recent noble gas that he's passed. So he passed krypton most recently. And then just the electron configuration that remains. So he's going to be in the 1, 2, 3, 4, 5. And then he's going to be in the S block, and he's going to be in the first. He's going to be the first electron. Okay? So this is the one for rubidium. Now, let's move on to the transition metals. How the transition metals are going to work is that, let's say what we want to find vanadium's electron configuration. What we're going to say is we're going to put down our normal things: 1s, 2, 2s2, 2p6, and then we're going to have 3s2, which is sodium and magnesium, and then we're going to have 3p6, and then we're going to have 4s2, and then we'll have 3d. Because remember, because in the D block only, the rows are 3, 4, 5, and 6. Okay, and I'll show you how that works with the lanthanides and actinides. So 3d, what electron are we? We are the third electron, so 3d3. So this would be the full electron configuration of vanadium. Okay. Let's try another example. Let's say we want to find the electron configuration of let's say silver. So let's use the noble gas notation for this one because it is very long. So the most recent noble gas was krypton. So we're going to put our krypton in brackets. And then we're going to continue. So we're going to be in 5s2. 5s2. And then we're going to be in the fourth row of the D block. And we're going to be the ninth electron. So we're going to have 4d9. This is going to be the classification of silver when it pertains to electron configuration. Now, let's see how the lanthanides work in this case. So let's say we want to know the electron configuration of lanthanum. Let's use the noble gas notation for now and realize that this section right here, this is where the lanthanides are actually supposed to be. So we're going to classify them as row 5 of the periodic table. And the actinides, we're going to classify them as row 6 because they're little empty spaces there. Okay, because there are rare earth elements. So let's use the most recent. Let's imagine that lanthanum here is in this row. This is row 6 of the entire periodic table. However, it's row 5 in the D block in the transition metals. So these rare earth metals, these count. These count as the same rows as the D block. So it's going to be 5 and 6. So we are going to have the most recent noble gas. So in this case, this is going to be xenon. And then we're going to have the electron configuration, and then we're going to have our row 6, and it's full, so 6s2. And then when we go over to our thing right here, we're going to have 5. We're going to be in row 5. We're going to be in the F block, and we're going to be number 1. Okay? And that comes before 5D, by the way, because as you can see, they're filled in on your periodic table. It says elements 60. It says elements 57, I think, through. Yeah, but it says that those elements, all of these yellow elements here on our periodic table, are before all of these. Okay. So this is the one for lanthanum. Let's try neodymium. So for neodymium, we'll have the most recent noble gas, which is xenon, 6s2, 5f, and which one are we? We are number 1, 2, 3, 4. Okay, so this is how you do the electron configuration for that. Now let's try the actinides. So let's say we want to find the electron configuration of einsteinium. Let's use the noble gas notation. So our most recent noble gas, we're in the 7th period, but we're in D block number 6, or D6, or 6D. So our most recent is Rn. And then we're going to have 7s, and then we're going to have 7s2. And then for our thing here, we're going to be in the 6, and we're going to be in the F block again. And for einsteinium, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We're going to be 11. So this is the electron configuration for Einsteinium. Okay. So, as a challenge, with using the noble gas notation, what is the electron configuration of tennessine? I'll give you all a few moments to solve that one. Okay. So, our most recent noble gas, Rn, and then we have 7s2, because we're in the 7th row, S block. And then we have 6F15, 6F15, and then after we get through all those, we have 6D10, or 6D, not 10, we have 6D9, because we have 9. Those other ones were part of the F block. And then we have 7P, and we are number 1, 2, 3, 4, 5. So this would be the electron configuration of a neutral tennessine atom. Now, let's move on to a different concept now. Let's say if we want to try to find the electron configuration of helium minus. So this is just helium with a negative charge. This is going to be different because the amount of electrons we have is different. So usually helium has 2 electrons, but now it has 3 electrons. So let's use let's use electron configuration to find what does this mean? What does the electron configuration even mean? So we're gonna have 1s2. What this is saying is that we have 2 electrons in the s, but we also have an additional electron. So we're going to be 2s1. So remember, these in a neutral atom, these are always going to add up to the atomic number. Okay? These are always going to add up to the atomic number. But in this case, we do not have a neutral. We have a negatively charged ion. So we're going to have 1s2, 2s1 as our thing. And notice it's the same as lithium. Lithium also has the same thing. So that's why on a test it'll specify what is the electron configuration, or like it'll give you an electron configuration, and they'll tell you a neutral atom or some sort of ion, and they'll tell you specifically what they're asking for, because they do have some of them do have the same electron configuration depending on their charge. So let's say we want to find fluorine 2+. Okay, fluorine 2+. So the electron configuration for fluorine 2+, all this means is that we're taking away 2 electrons from fluorine. So we're basically going to have the electron configuration of nitrogen. So let's just fill that out. 1s2, 2s2, and 2p3. So this is the electron configuration of F2+, or fluorine 2+. Now, let's try another example. Let's say we want to find chromium, chromium 2-. Okay. So for chromium 2-, we're adding 2 electrons. So we're basically going to have the electron configuration of iron. So let's use the noble gas notation first. Argon. And then we are going to go down with 4s2. And we're going to be in the 3Ds. And then we're going to be number 1, 2, 3, 4, 5, 6. We're going to be number 6. So this is the electron configuration for Cr2 minus. And just a quick challenge problem here. What is the electron configuration for xenon minus? Or sorry, plus. Xenon plus. What is the electron configuration for xenon plus? So we probably want to use the noble gas notation. So our latest noble gas is krypton. And then we're going to have 5s2. And then after that, we're going to have our 4Ds, so 4d10. And then after that, we're going to have our 5Ps, and we're going to be basically the same as iodine, because remember, when we're positively charged, we lost an electron. So we're basically going to have the same as iodine. So we're going to have 1, 2, 3, 4, 5 electrons in this orbital. So I hope everybody liked this video. This was a comprehensive video about electron configuration of atoms. I hope everything was explained very well. And this concept, very crucial in understanding quantum numbers later on. So I hope everybody will get this. It takes some practice, but you'll get it eventually. All right, everyone. See you later. Goodbye.